Morning, good afternoon, or good evening. Welcome to the topology optimization webinar. Today is our 32nd session, and it is dedicated to Truss optimization. It's kindly organized by Dr. Helen Fairclough from the University of Sheffield. Helen has given a presentation in top webinar in one of the very first ones in 2020. So it's really nice to see you again and to host a session dedicated to Truss optimization. So thank you, and please take it from here.
Okay, thanks very much, Jun. So I will share my screen. So I'm going to start, as has been the format for this year, with an introduction to the topic, and then we're going to have two presentations on recent papers, in this case from Jonas Warmuth and Enrico Stragiotti, who I'll introduce afterwards. But I'm going to start us off with an introduction to Truss topology optimization, and some of what I'm going to talk about is based on a recent paper that I've written specifically about applying this to elastic compliance design. But I'm also going to give a bit more of a general introduction as well. So it's not going to be limited to just that. Okay, so I'm going to start off with a bit of an introduction to why we should care about trusses, and also from my background, why the built environment is a particularly interesting topic. And then I'm going to go through an introduction to some different problems, kind of in order of difficulty, starting from some reasonably easy ones and getting more complicated. So I'm a civil engineer by background, and I obviously think it's very important that we should apply optimization to buildings and bridges. One of the reasons for this is that actually it's a huge contributor to global warming, CO2 emissions. Just the materials, the concrete, the steel that we use in construction is about 11% of global emissions. Never mind things like heating the buildings that we can also influence. And it's more than just the carbon, it's also just a lot of stuff. So it's a lot of the amount of material that we've made as humans now is more than the total mass of all living things, so every tree, animal, etc. And all of that stuff has been either dug up from mines or in the ground or dredged like sand out of rivers and the sea. So anytime we're doing that, we're destroying habitats, we're polluting water, air, and we're creating a load of things that are going to eventually end up in some sort of landfill. So hopefully I've convinced you that we should think about applying optimization to the built environment. But you're maybe thinking, why can't we just use topology optimization as we're used to? Well, there's a couple of key features of buildings and other infrastructure that make it challenging to apply topology optimization. By no means impossible, people have done it, but maybe not the easiest way to go about it. The first being that if you look at buildings, bridges, etc., the actual elements are very small compared to the total space that it makes up. So for example, in a suspension bridge or a cable stayed bridge, you're going to have cables. They're going to have a diameter that's something around the order of maybe 5 centimeters for those vertical cables here. And the bridge itself might be 1 kilometer, even 2 kilometers long. So you'd have to have some crazy high resolutions in continuum topology optimization to be able to break that 1 kilometer long domain up to be able to see a 5 centimeter wide cable, let alone the difference between having a 5 centimeter wide cable compared to a 6 centimeter wide cable, for example. So that's the first thing, is it's just you'd have to run things at really high resolutions to solve real problems. The second one that's a bit more conceptual is that you can't really put an entire building or a bridge on the back of a lorry in one piece and take it to where it needs to be. The only real way we can get these structures to where they need to be is to take them in smaller pieces. So we could take our continuum optimization result and chop it up, but why not start from something where that's intrinsic to the method? So in this slide, I've tried to summarize the main differences between truss or frame optimization and continuum topology optimization. Obviously, I'm sure most of you are aware, continuum topology optimization is a huge field. As John said, this is the 32nd one of these topology webinars, and the majority of them, the presentations have been on continuum topology optimization. Truss optimization could potentially be just as big. It's had slightly less interest, but absolutely covers the same scope. And the main difference really is that instead of having a basic element that is a 2D triangle or pixel, or a 3D cube, tetrahedron, etc., our basic elements are lines. So a linear truss bar. As we said, this makes it more suitable for manufacturing it by assembling it. We can take all these separate linear elements and attach them together, rather than the kind of additive manufacturing or even kind of milling, subtractive manufacturing approaches that get really challenging at building scale. It's more suitable for the lower volume fractions, although you will see there, obviously these are very approximate numbers, but there is a gap in the middle where neither side works amazingly, which is kind of an interesting sort of edge case. And again, just as there are for continuum topology optimization, there are several methods for truss optimization. However, by far the most common and most kind of frequently studied is the ground structure method. So that's what I'm going to talk about today. But other methods, such as growth methods, you'll also find in the literature. So the ground structure method follows a process shown in these diagrams. So we start, just like with topology optimization, with some supports, some loads, and a blank space that we want to fill with structure. The difference comes, so instead of discretizing that with some sort of mesh, we discretize it by putting some joints spread through the domain. And now this is just a very low resolution illustration. In reality, there'd be hundreds, if not thousands, of those points. And then we connect each pair of points with a potential truss element. So that's what that structure then with the potential connections is what we call the ground structure. And then we solve an optimization problem to find out usually what should be the cross sections assigned to each of those potential elements. And typically what we find is the majority of those elements, the cross section they should have is 0. So in other words, they shouldn't exist. So we end up with just a subset of the members that we actually need in our final structure. Okay, so with this now, the big question is, how do we actually formulate that problem to find those cross-section areas? So quite frequently in truss optimization, there's a lot of useful formulations that are actually convex. So that means that the shape of the constraints means that there's no extra local optima that are going to trap that optimization. So the green shapes on the top row there, if you just keep heading downwards, you get all the way to the bottom. They're convex. The moon shape and the L shape at the bottom, if you start somewhere and just keep heading down, you can maybe end up in the corners and you can't kind of jump out of there. So because we're looking at problems that are convex, it means we always get that global optimum. And it means that generally the easiest way to solve this is to put the whole problem, the analysis and the analysis variables and the design variables, and put it all into one solver. So for convex problems, there are some very quick off-the-shelf solvers available where you can solve things with hundreds of thousands of variables in a few seconds. So the first couple of formulations I'm going to show you are ones where we can do this. So probably the most common formulation that you'll see, the one that people tend to start from in truss optimization, looks like this. So our problem, we've got variables A and Q, so they're cross-section areas and axial forces for all those different bars in the ground structure we saw before. Minimizing a volume that we're calculating with length times area for each bar, and subject to our constraints on equilibrium. So we have a matrix here called B that basically just resolves those axial forces into horizontal and vertical components and out of plane components if it's a 3D problem. And we say that needs to balance our external applied forces. And we have some stress limits in tension and compression that say our areas have to be large enough that we've not got stresses that are too big. So this is typically called the rigid plastic formulation because it doesn't explicitly enforce elastic compatibility. But if we're just solving a single load case problem, then we find that the same topology is optimal for any material model. So this is your classic Mitchell structure or fully stressed design. All the bars have the same stress and the same strain. So it doesn't really matter what material model we're using. We might also want to look explicitly at compliance optimization. So in this problem, you will see a lot more variation in exactly how it's posed. This is my preferred way of doing it. So I like to stick with the same posing of the problem in that we're minimizing volume subject to a limit on our compliance or our total elastic energy. So we keep pretty much the same objective value. We keep the same equilibrium constraints. We add in a new variable here, we've called it P, for the elastic energy in each element. And then we can sum those up to get the total elastic energy, which we know is going to have to be equal to the compliance because internal work and external work need to be the same. So the other major variation that you'll see is to minimize compliance with a fixed volume. So that's a little bit more similar to what's commonly done in the continuum side of things. The reason I'm not so keen on that is it doesn't match what happens in certainly civil and structural design in practice, where we know usually a displacement, but something similar to a stiffness that we can have, and we want to know how little material we can do that with. But you can swap around, as shown here, the objective and that constraint. It's still a convex problem, and you get the same layouts if you're doing the worst case compliance. So that is also totally valid. So a few results here. You can see that with a multiple load case problem, so in this case, we've applied those 3 loads in separate cases, we actually get different results for a rigid plastic versus a compliance problem. And it's quick-ish. So this one here has 250,000 potential elements, but it did take about an hour just on a normal laptop. So we're not talking supercomputer time, but it can be quicker. So the single load case version actually only took a minute to solve. And the way we make it quicker, or a way to make it quicker, is to use what we call member adding, or what mathematicians would call column generation. So a quick geometric example to sketch the idea of this. There's not going to be time to go into huge detail mathematically, but if we say we're trying to find the lowest point in that black region, so inside the circle and the square. Okay, clearly that's the point with the green X. And now we want to solve a related problem where we've got an extra constraint that the point has to be inside the blue triangle. Well, is it going to have changed? We know that we've not added any new areas that this optimal point could be in. There's no new black areas. We've just removed some that are shown in purple. And that point that was the best before is still valid. So we know that we can't improve it. It was the optimum before. We've not added any new, potentially better places we can go. So we can't possibly have improved it. So we know that that original point is guaranteed to be the optimum for the new problem. And that's essentially the idea behind member adding, is that we're adding our extra constraints, but we know we don't need to add them because we know that adding more constraints can't improve the problem. So essentially the only sort of trick with this is that you need to write your problem so that each element or each member is represented by a constraint. You'll have noticed that that isn't really what happened in the formulations I just showed you. We had our members represented by variables, the cross-section area, the axial force. So usually what we have to do is to take the dual, so that take the Lagrangian of the problem as we would formulate it. And then we can apply that same idea as with the shapes. And we get a result that looks something like the one on the left, where we can go through different iterations, adding members. And actually, that result on the left is massively slowed down to show you the steps. If you go and set that up on Layopt, which is our web app, you'll see it solves in like a second or two. So does it make a big difference? Well, speed-wise, yes. So it makes no difference to our final results, but in terms of speed, well, the one before that was taking about an hour is shown in this graph with the white filled points. If we solve it with member adding, it takes about 30 seconds. So that's a speed up of about 150 times. On the laptop I was using, I couldn't actually solve anything bigger than that one, any higher resolution on my laptop, because it ran out of memory. I couldn't store the whole problem. So I couldn't solve them. But if we extrapolate that fairly nice straight line, the largest problems that you can solve in under an hour with member adding would have taken an estimated 1.2 years to solve if you just tried to do it directly. So it makes a pretty huge difference, particularly for higher resolution problems. And we can apply this to a pretty wide range of things that are convex that I don't really have time to go into now, but there are quite a surprising array of different problems, if you think about them the right way, that can be made to be convex. But obviously not everything. So for a non-convex problem, there are various strategies we can take. So you've probably all come across evolutionary algorithms, other meta-heuristics, gradient-based, where we just choose a starting point and try to improve from there. The approach that I tend to prefer for these more challenging problems is a kind of two-step approach. So it's illustrated in the larger graph on the right there, is to solve a simplified problem. So generally one of those ones on the previous slide, get a lower bound there, and then use that as a starting point for the more complex one. So the simplest application of this is in geometry optimization or shape optimization. Essentially, we're just adding the positions of those joints as variables, as you can see on the example here. So it tends to make a pretty small difference in the volume, less than 1% in most cases, but a big difference in how nice your results look and how much you can understand them. We can also do an automatic simplification kind of approach. So similar to that, except we're, instead of minimizing volume now, we're going to minimize some measure of complexity. So for example, number of members, things like that, with a limit on how much volume increase we're happy to have. And there's a huge range of other numerical factors, some of which we're going to hear a bit more about from our other presenters today. And there's also, this second step doesn't have to be a mathematical problem. So another thing we've been experimenting with is what we're calling human in the loop modification. So essentially, what if the problem with your solution is it's just not pretty enough. It doesn't aesthetically work. So this lets you have a second step that involves a human making some modifications and then iterating that with the machine. Okay, so a summary of what I've been saying. So we need material efficiency in the built environment for net zero, and truss and frame optimization is really the most applicable thing for that. Although, as we'll see from some of our later presentations, it can be useful outside the built environment as well. And a surprising amount of useful problems in truss optimization can be posed as convex problems if you think about them in the right way, which means that it's fairly quick to solve them with just off-the-shelf solvers, and really quick if you can get member adding going. If you've got problems that really aren't convex, then a two-step approach is often useful, and still it's often quite helpful to have those still as a simultaneous analysis and design. So to have all of your analysis equations built into your optimization. Again, it's quite a wide field, so I'm not saying that's always the way to go, but it's certainly, if you're doing a truss problem, it's certainly always worth thinking about, I would say. So that's it from me. And I think, on which order we're doing things. So we're going to have Jonas presenting next.
Yes. Let me quickly share my screen. Okay.
So Jonas is from the EPFL in Switzerland, and he's going to tell us something about design and exploration of low carbon structures. Thanks, Jonas.
Yeah. Thank you very much, Helen, and thank you very much for the invitation to the top webinar. Yeah, as you said, I'm from the EPFL and I'm a PhD student there at the Structural Exploration Lab. And yeah, in my presentation, I basically would like to speak a bit about designing and exploring low carbon structures. Why low carbon structures and not low cost or low weight? Well, the answer, you gave it already, Helen, is because of the construction sector and its environmental impact. Yeah, and its emissions. So the construction sector or the related construction things are accounting for 11% of all global CO2 emissions. And if we also include the operations of buildings from our built environment, it's up to 40%. So clearly, we as architects and engineers, we need to do something about that. And we need to think of solutions that lower the environmental impact of our structures. And basically, there are three strategies to do that, where the first one is to use low carbon materials like timber or rammed earth. The second one is to use resource efficient design. So this is really going into the optimization direction and what we've just heard from Helen. And the third one is about following the ideas of a circular construction. So for example, to reuse structural elements over multiple service cycles. And in my presentation today, I would like to focus a bit on the last two, so on resource efficient design and on circular construction or on reusing structural elements. So starting with the first one, when we speak about resource efficiency, optimization is a very nice way to do it. And when we speak about trusses, layout optimization and the ground structure method is a very nice way to do that. How it works was basically explained by Helen already, but just to maybe give you a quick reminder, we start with some boundary conditions, so a load and support conditions. We then add a grid of nodes and we interconnect those nodes, which is then our ground structure. And then we run a layout optimization that aims to minimize volume. And we would end up with a structure, for example, like this on the right-hand side, which is then the most efficient structure for the boundary conditions that we gave. So, but when we design structures, we also want to know, or we want to explore different shapes. We want to know what is possible, what is feasible, what does look nice. And layout optimization is good in giving us efficient results, but it's not so good in giving us these alternatives, because I could maybe make my grid of nodes denser, but the structure would always look the very same. And this is why we try to basically customize this approach a bit. And this also goes in the direction of what Helen said about putting the human to the design loop. And what we did is basically we said, okay, let's take the ground structure approach, but let's decide, the designer or the user, where to place nodes. So as for example, here on the left-hand side. And out of those user-placed nodes, we then create a custom ground structure, and we run a layout optimization that will deliver us a structure in equilibrium. On top of that, we could also, for example, define some goals like some length bounds or force bounds. But in general, it's really about placing those nodes. And in the end, we will get a structure that we wouldn't find with the conventional layout optimization approach that I've just shown you. And when we then remove or move or add nodes, we can come up with different solutions and different structures and basically different shapes, which is what we want. But the good thing is still that since we use layout optimization as the ground approach, we always get efficient structures, which is important for us. And if we think of the example that I've just shown you, which is here on the left-hand side, we can then also find other typologies, other types, other forms. And this really allows us then to explore different designs, which are all still performing quite well. So we implemented that basically into a Grasshopper tool, just to give you a little impression how it works. You basically define your supports, you define your loads, and then you can just add nodes as I've shown you. And then you will directly see what the resulting structure of the nodes you've added is. And the nice thing about this layout optimization is that it works in real time here. So you can quickly explore a wide range of different structures with different topologies, different shapes. And the idea here is that you can basically play around and see what the impact is of when you move nodes or remove them. And of course, this doesn't only work in 2 dimensions, but also in 3 dimensions. So for instance, here, this is a little bridge example with an arch bridge. And we can, of course, extend that to a 3-dimensional space and do the very same. We can move the nodes around. We can see what is the impact of our action that we just did. And by this, we can get an idea of what structures are possible for the boundary conditions that we gave, and what structures actually make sense. And if we think this example of this bridge a bit further, we can basically find a wide range of structures where most of them perform very well, but at the same time, we are able to explore a lot of different shapes. And this way is basically the way we do, or we address resource efficiency in design. And now let's quickly talk a bit about the second strategy that I've shown you in the first slides, which is reuse. Reuse is also a technique to lower the environmental impact of our structures. And just a little example, what it means is that we take elements from structures that are obsolete, that are about to be disassembled, as for example here an electric pylon, and then we take these elements as an input for a new design. So for example, here on the right-hand side, we try to design a new roof structure for a train station. And of course, this is not straightforward, so you need some computational support to do that. Some computational support that tells you where to put which element in your new structure. And when we talk about reuse, we also need to talk quickly about 2 major things that are important. The first one is that when we try to approach reuse, we have a change of design paradigms. So in conventional design, we usually design our structure and then we manufacture the elements, right, that we need in order to build the structure. But in reuse, it's really the other way around. The elements are already there, and we need to find good connections, a good overall layout for our structure, such that it makes sense. And the second thing in reuse is that we usually aim for hybrid solutions. So 100% of reuse is in general infeasible because it would end up in a very highly overdimensioned structure. And so we try to add from time to time new elements as well, because this in the end gives us really the structure that has the lowest environmental impact. All these ideas from reuse, we also implemented them in a computational tool, which is called Phoenix 3D. And this basically allows you the very same as I showed you with the layout optimization. So I think I have a quick, yeah. So the idea is that you generate a stock of elements that might comprise reused and new ones. And then you try to optimally assign them to a structure that you're trying to design. And while you change the structure itself, you will directly see what the impact is on the stock elements that you are using. And whenever you make changes, you will get the real-time feedback on what impact it has. And so we have basically a tool that allows you also to check in real time how well does a structure fit to a stock. And what we can now do, and this is the nice thing basically, is we can combine those two approaches. So I've first shown you a nice way to explore resource efficient structural forms based on layout optimization and this modified ground structure approach. And we can now combine that with the idea of reusing structural elements and of optimally assigning them to a structure that we aim to design. And so we can combine two strategies to lower the overall environmental impact of structures. And if you think of this bridge example that I showed you for the layout optimization, we can apply that to the reuse case as well. And we will directly get an idea of which structures do fit nicely to a stock of elements that we have, or which maybe not. And no matter which structure we try, we already know it's somehow a well-performing resource-efficient structure because we got it from the modified layout optimization. So some time ago, we had the chance to use this approach or to use some of these findings in a real build project. And the idea there was to generate the facade structure that you can see here. So the general concept was to have it as a tree-like structure, and it should be made out of reused steel elements. And those steel elements, they were coming from disassembled electric pylons in Switzerland. And so the architects provided us with the characteristics of those elements, so their length, their cross-section, their yield strength. And out of that, we could provide the architects an early version of the approaches that I've just shown you, an early version of the computational tool. And so the architects could play around with their design, with their facade structure, and they would always directly see which impact it has on the utilization of the stock elements they have, on the overall structural performance. And by playing around, they ended up in their final design and in the way they really wanted to build it. And after that, the structure was actually built. So here you can see how the final result looks like. And here's a closer look. So you can see there's also some connection sheets that are not in use that indicate basically that those elements were used formerly slightly different. But so overall, we can use layout optimization as a basis, let's say, to design environmentally sustainable structures. Yeah, thank you.
Great. Thanks very much, Jonas. That was, really interesting. Great results. So we're going to jump now into Enrico's presentation, and we'll come back for questions and things at the end of all the presentations. So if you want to share your screen, Enrico. And while you're doing that, Enrico is from ONERA in France, and he's going to be talking today about a slightly different application. He's going to be telling us about Truss topology optimization for aeronautical structures. Over to you, Enrico.
Thank you very much, Helen. Thank you very much for the invitation. So my name is Enrico Stragiotti, and today we'll present to you my research entitled Efficient 3D Truss Topology Optimization for Aeronautical Structures. That has been recently published in the SAMO journal. And so, basically the context in which my research is based is in the aerospace engineering field, where in general there's a continuous need for lighter structures. This is due principally new environmental issues that ask for, in general, solutions. So new propulsion technologies that are usually heavier. We can see here some of these concepts. And the common thing about all these concepts is that in general, they are really different from the classic tube and wing architecture of modern aircraft. And so there's a need really to redesign the sizing software that we use. So in general, there's a need for ultralight structural optimization that is tailor-made for this new concept. When we talk about structural optimization, we absolutely need to talk about effectively topology optimization, so continuum-based topology optimization. And as already Helen have explained to us, in general, as we are reaching a very light structure, so with a very low volume fraction, we arrive at the moment in which the size of an element is basically a limit for our structure. So we can basically do what has already been made in the literature, so to use a really fine mesh, but these usually ask for a lot of time, and usually in the conceptual phase of aircraft design, we don't have this much time. It's for that reason that we decided to use Truss topology optimization. So I won't enter again into the details of how Truss topology optimization works, but the idea is just that it's based on the ground structure. So here in gray, and the idea is that we want to size the strut of this ground structure in order to sustain the load that we give. Is usually formulated as a volume minimization problem with stress constraints, but in later years, the Truss topology optimization formalization has been extended in order to take into account multiple mechanical constraints. As for example, here we can have an example of structural stability or even flatter aeroelastic analysis. So the idea and objective of this presentation is to build on this contribution and to formulate and solve a unified volume minimization problem for 3D truss structures. And the idea is to take into account multiple mechanical constraints, as for example, stress, but also local backing constraints and minimum slenderness. And then we also want to take into account multiple load cases, as we will see in the aeronautical domain is very important. An additional constraint that we want to add is that we want it to be fast and also reliable. So we want to have a lot of problem with the local minima. So let me present you a little bit more the Truss topology optimization formulation that we propose. It's a volume minimization problem with nodal equilibrium constraints. So basically we want that the loads that are generated by the external loads are actually the sum of the loads are 0 in every node. We want to take into account the kinematic compatibility. So we basically, to put it in a simple way, we want that hook law is verified at the bar level. We then want to take into account local backing constraints, because as you can see here on the image, for ultralight structure, it's definitely a failure mode that need to be taken into account. We want to take into account stress constraints as well. And as I've said, we want to have a minimum slenderness for the bar, as we don't want to have a bar that are too thick. Yeah, we basically want it to stay in the domain of the discretization we are using. This formulation then has been modified to take into account the multiple load cases. So as for in this example, we want that the structure can take concurrently the load P1 and the load P2. And the problem with this formulation, that it is in general non-linear and non-convex. So as Helen already explained to us, have a lot of problem with local minima. We can, it is for this reason that the main contribution of this paper is effectively, as Helen already suggested, is to propose a two-step resolution algorithm. The idea is that once we have our boundary condition and the initial ground structure, we solve at the beginning a relaxed problem with linearized backing constraints. And then the solution of this first problem is used to simplify the ground structure. So basically to restrain the design domain of a second optimization in which we restore all the constraints. So if you want to go a little bit more into detail, the original formulation is relaxed by not taking into account compatibility at the beginning, and also by linearizing local backing constraints, as we can see here on this image, in which the quadratic backing constraint, local backing constraint, is linearized. In the paper, we go a little bit deeper into details, and we propose also an heuristic to try to reduce the problem of local minimum, but I won't enter into details right now. And this problem, as is written, is actually linear, so it can be solved using an SLP. So it's not linear, but is easily linearized, so it's using sequential linear programming. The solution of this first relaxed problem is then used to simplify the ground structure. We can see here the solution on the right and the initial ground structure of the first problem on the left. What we obtain by doing a thresholding is this image, and this is going to be the ground structure that is going to be used in the second problem. With actually a complete nonlinear programming formulation, and in our case we use the IPOPT algorithm to solve this second problem. So if you want to actually assess the quality of this algorithm, we first have to see what will happen if we are not using the proposed methodology. So I show you here a really simple load case, so a 10-bar truss with only 10 bar. And we see that if we solve the original formulation with just a nonlinear program, nonlinear programming optimizer, we would obtain a very different structure based on the starting point. We can see it a little bit better on this graph, in which I plotted the starting point, so the volume of the 50 different starting points, so the black circles, and then for every circle there's the solution that we would obtain with NLP. As we have a very different volumes, this is going to tell us that in general only 20% of the 50 different points actually converge to the best solution found here in this case. But once we use our proposed model, we see that actually we actually have a 100% converged solution to the less voluminous structure. So now that we have validated this methodology on a very simple dummy case, we can now apply it to a more complex aeronautical load case, in which the main difficulties are the fact that the structure is actually pretty large. We are talking about a wingspan of almost 60 meters. We are talking about a structure that is loaded with 3 different load cases. And we are using here an aluminum alloy to actually solve the problem. The objective of this optimization is to compare with what we find in the literature. Actually, we are comparing our work with the one of Fakimi and his research group. And the idea is that we are using the same exactly ground structure and load cases. We just need to highlight that there's a big difference between us and them, because they are using a discrete cross-sectional arrays, and also they are performing sizing optimization and not topology optimization. So we won't have any bar that have a section that is equal to 0. So I can present here to you the solution of our algorithm. We can see here also the deformation of the structure for the first load case. And if you wanted to compare it with the solution of Fachimi, we found that in general, we have a 27% improvement in mass. This is essentially due to the fact that we are using continuous section, but also especially because we are doing topology optimization. So we have for a 350 member in the ground structure, in the solution, we have only 250 that are active at the solution. And then, most importantly, this is a solution that has been generated in a little bit more than 2 minutes on a regular notebook, while in the case of Fachimi, it was more than 4 days of calculation. So as the calculation time was pretty low, we decided to explore a little bit some more complex ground structure. We have here a ground structure with almost 10 times the number of elements. So it was 2,370 different members. And we see that the solution actually is not only lighter, but was also stiffer, so suggesting that in general, we found a more efficient structural topology. And you can see here on the right, the 3 load cases. So we have on the top the first and the other on the bottom part of the image. And we have on the left part of the image, the stress, and on the right, the buckling constraints, so where they are active. On the paper, we analyze a little bit better also which are the most important constraint for this specific problem, and which is the load case that actually constrain the most the structure. But in general, I won't get into details here. So to conclude this short speech, the main objective of this work that we accomplished was to develop a design methodology for ultralight structures that was applied to aeronautical structures. And we made it by first formulate a 2- and 3-dimensional truss structure mass minimization problem that was subject to multiple mechanical constraints, such as maximum stress, topologically, buckling constraints, and minimum slenderness. We take also into account multiple load cases. And then, most importantly, we develop actually a 2-step solving algorithm that improved not only the speed, but also the robustness with respect to the sensibility of the initialization point. So thank you very much for your attention.
Thank you very much, Enrico. That was really interesting. So now we come to the question and answer part of the session. So at the bottom of your screens, you should be able to see an icon marked chat. So feel free to type questions in there. Or if you'd like to verbally, I believe there's a button marked something that where you can indicate that, and one of our kind tech Niels or Jun will be able to give you permission to speak. But I see we already have, while you're thinking, we already have a question in the chat. So we have a question from Martin Pierre that says, thanks, Jonas, for the nice presentation and demos. And he has a question about the first part of the presentation on user place nodes, where he's noticed that the ground structure was not always fully connected, and asks, what was your strategy to choose whether to connect a given pair of loads?
Yeah, thanks for the question. So basically, I also showed that we can apply some goals, which we would formulate as constraints for the layout optimization. And one constraint could be to set an upper and a lower bound for the length of the bars that I have. So the straightforward way to do that would to really include this as a constraint into the optimization process. But a slightly smarter way is to simply check before the ground structure if bar lengths are within the boundaries that I gave, and simply remove all the ones that are not within those boundaries. And this then leads to those ground structures that are not fully connected, because they follow the boundaries on the length of the bar elements that I gave. And so by doing that before running the actual optimization, I can more or less save some computational complexity, I would say. So I maintain it to be real time.
Excellent, great. I think that hopefully answers your question there. So I see
thanks, Jonas.
Peter Dunning has put his hand up. Can you unmute yourself? Yes, there you go.
Hello, I have a question for Enrico. Very nice presentation.
Yes.
And some very nice results. I was just wondering, did you include the upper and lower skin panels in your model at all? Because those carry a lot of the load in an actual wing structure.
Yeah. So no, in this case, no, because this was during my PhD thesis. We didn't have the time to take this into account. So it was just the optimization of the wing box, actually, of the aircraft. But the fact is that like the loads that we were using were already the loads transmitted by the wing to the actual the box, the wing box. So I'm almost sure that like in this specific case it would be the same. Just because the loads that I'm sorry, no. The loads, so yes, the loads were generated without taking into account the shear that is transmitted in the panels. So yeah, it's a simplification that we actually made.
So it'd be nice actually to include the sizing of the panels on top and bottom and the same time.
Yeah,
okay.
It would be cool actually.
Thank you.
Thank you very much for the question.
Great, thanks very much for that question. So Yakov Zelikman has put a question in the chat that he would like to ask Jonas about the loads that the facade structure in the last example was optimized for.
Yeah, very good question. So initially when we were setting up the model that we then provided for the architects, we were accounting for self-weight and for horizontal wind loads, so vertical self-weight and horizontal wind loads. But I need to admit that in the end, the build structure was just built geometrically and in a way that it wouldn't be self-standing, even though we designed it in a way that it would be self-standing. But so yeah, overall the loads that were included were self-weight and wind loads.
Great, thanks very much, Jonas. And then Fabian has a general question. And he's asking whether there are approaches to model joints with more detail, such as the stresses within joints. So there are various approaches about joints. Obviously, it's very different for different construction types. This is something that's very specific to the materials, etc. Typically, the simplest way to do it is to kind of include sort of costs for things that you know are bad about joints. So either just having more joints to add some cost there. There is some initial work that I've seen about that can kind of combine the truss optimization with more continuum bits in areas such as joints. But yeah, I think that's still kind of quite an interesting area, partly just because of how general, also how varied that can be in the different approaches. I don't know if Jonas or Enrico want to say any more about that.
No, you covered it, I guess.
That's fine. Daniel, then, I think you're next. I think you're not unmuted if you're trying to speak, Daniel.
Sorry about that. No, great. No, I was just saying great presentations, and I was chatting to one of the designers of a new skyscraper in London recently, and it's called 55 Bishop's Gate, I believe, and on the side of it, it's got a lovely Mitchell Truss design. And when speaking to him, he said that he'd used layout optimization and things like this as part of the design process. However, he felt that there was a bit of a gap, say, between the theoretical tools and actually the practical side. And it was interesting to see the human in the loop, sort of more sort of practical things, more tailored to perhaps to the design project. Have you sort of thought about any more about bridging that gap between sort of trying to teach industry technicians about layout optimization? That was my first question. My second question is, have you thought about any kind of machine learning assisted tools or approaches?
Yeah, great questions. So to take them in order, yeah, chatting to industry, I think it's one of those things where things are moving quite quickly. Certainly not so much myself, but certainly my PhD supervisor tried going around to industry 20 years ago and saying, would you like to do some optimization? And everyone just sort of went, what? Whereas now there's a real willingness to talk and to sort of discuss what are the needs. So that's really great that the enthusiasm's there. And as you say, I think there's always going to be an element of it needing to be the human in the loop type things, because you sometimes, either whether that's the sort of after the optimization, which we've got implemented in our Peregrine digital tool, or whether it's Jonas's approach where you're setting the customized ground structures, just because a lot of these things you don't realize what you want until you see it. And it's complicated things like, oh, but we can't put that element in because that other element's in the way, and where's the crane going to go, or something really specific and almost impossible to say in advance, I think. So I think, from my side, certainly that's a part of it. Jonas, do you want to say anything? Or Enrico, but I guess this was a bit more of a...
maybe I can add a few things. So, I mean, also maybe addressing the machine learning question. Of course, this would be a powerful approach, and this is already also done by other researchers. But the way we approach it, or we want things to approach, is always that the human fully decides what he or she wants or doesn't want, and that you also understand your design task while you're doing it, what Helen just said, and that you also develop an intuition for yourself, what is feasible and what is infeasible. And we feel that this is better achieved if you really let the human do all the work, such that the human can understand the design task. Because when you start the design task, you don't even really know what the design task may look like. And by adding machine learning, you would skip that process a bit. You would skip this intuitive understanding of what your design task would look like. But for sure, you could add it afterwards, I don't know. But really for these first steps, for these conceptual steps, when you try to understand what you're doing, we think that really putting it as clean as possible is the best way to go.
Yeah, interesting. Sort of the things that I was thinking about when you were in your presentation were perhaps the optimization algorithm might run alongside, say, a bank of common connections, and then which are commonly used rather than, say, bespoke parts, and there might be some kind of interface. I don't know, to kind of perhaps reduce the cost. Maybe perhaps the lowest optimum isn't the cheapest, or and things like this. But great points. Thank you very much.
Great. So we're coming to the end of our time here. I think Martin has one more final comment, that a common result of adding the human in the loop is that the human finds a way to override the loop. I think that's probably true, but I think, as Jonas was saying, that's not necessarily a problem. If we've informed them, if they've decided, there's a difference between using twice as much material as you need to because you've chosen to because it's cheap, and using twice as much material as you need to because you didn't realize you were. So I think at the very least we can have informed. So I'd like to draw the session to close, and thank you so much everyone for coming, and I hope it's been informative. I'm always happy to receive questions via email, etc., if anyone's got any things remaining. And thank you very much to Jun and Niels for having us at your webinar.
Thank you very much.
Thank you for the great presentations and for the lively discussion. Just a short announcement. Next month, on the 24th, we will have a session on industry topology optimization in industry. So hope to see many of you there as well. Have a nice day or nice evening.